Hi everyone, and welcome to discussion 7. So just some quick announcements. Electronic homework 6 is due Monday, which is tonight, or depending on when you're watching this video. And then project 4 on tracking has been released, and it's not due for a while, but I just recommend looking at it early on just to kind of gauge how the project is. And then for today's worksheet, the focuses will be on how to do variable elimination and like what you can get out of it, as well as some like independence relations regarding Bayes nets. Cool. So on the first page of the worksheet, you will see like kind of an overview of probability and Bayes net representation. And this is actually the same overview as last week. So I'm not going to go over it, but feel free to read over it and use it as a resource if you need it. So that being said, I'm just going to go directly into the problem of variable elimination. But before actually going through the problem statement, I just wanted to kind of point out some things regarding variable elimination. So with variable elimination, kind of like your two main steps are to do something that we call a join and something that we call eliminate. So these are the two main tactics that you are going to use with variable elimination. And more specifically, a join is kind of when you get the joint probability up to variables by multiplying the conditional probability. So specifically, if you want the joint probability of x and y, that will be equal to the probability of x given y times probability of y, and that is also equal to the probability of y given x times probability of x. So you will usually want to look for these types of relationships in order to join the variables. And then for actually eliminating the variables, you will need a summation of some sort. And you'll specifically be summing over all the possibilities of the variable you are trying to eliminate. So an example of how that looks like is, say you want the probability of x, but you have right now the probability of x and y, and you want to somehow eliminate y. So how you're going to do that is you're going to sum over all the possible y's. So usually when you sum over, you write out the lowercase just to differentiate between the actual random variable versus the values. And that means in this like probability, instead of writing capital Y, you'll be writing lowercase y. So then based on this, you will be summing over all the possibilities and just end up giving the probability of x. And in case you didn't see last week's video, I just want to quickly point out first that this is how I personally just write probability with like the double bars of the p. So all that means is just probability. To me, it's just easier to differentiate between like p the variable, which is why I write it like that. But yeah, cool. So kind of based on those two techniques, let's dive into variable elimination. So the problem statement is that we have this Bayes net here, and we are trying to compute probability of y given positive z. So we have observed positive z. And then all the variables have binary domains, and we want to run variable elimination in this ordering of x, t, u, v, w. And yeah, so let's get started. So they've already written out the factors that we start with after inserting evidence, which are these factors. And if they didn't give these factors, you would just look at the Bayes net and determine what probability tables there are. And remember, in the Bayes net, if you have a node, the probability table will just be that node given its parents, which is why, for example, if we look at node u here, the table we have is probability of u given t, because t is u's only parent. Cool. So these are our starting factors, and now we're going to start eliminating. And part A has actually already been given to us as an example, so I'm just going to quickly talk over that, and then hopefully that will kind of get you the idea of how we do variable elimination. So right now we are next going to eliminate x and generate a new factor f1. So since we're eliminating x, we want to go through our current list of factors and see what factors have x in them. And it's essentially just a p of probability of x given t and a probability of positive z given x. So what we can do is multiply them together in the join, kind of like how I talked about earlier, and then sum over them to actually eliminate the x variable. So that is how we get this expression right here. Cool. So then now we have the factor positive z given t because we multiply these two together, which will give us the different values, and then we sum over them and eliminate the actual x. And then this new factor will end up replacing the two factors as we used before. So that's why our remaining factors are the other 5 factors, and then plus the new factor f1. Cool. So now let's continue eliminating and go on to part B, where we are going to eliminate t. So first we want to go through our current factors and kind of see what factors have t in them. So we see that we have the first one, this one, this one, this one, and the last one. So all those factors have t, and to actually get a factor together, we will end up having f2. And I'm going to leave this blank first because we don't know what terms are going to end in them. But then that is going to be equal to these factors multiplied together. So probability of t, probability of u of t, probability of v given t, probability of w given t, and then f1 of positive z given t. Cool. So we see that for all of these t's are the given or the actual, so we actually still need to sum out to actually eliminate the t. So how we're going to do that is just sum over all the possible t's. Since we're doing all the possible ones, it would be lowercase t's. So actually when I wrote this out, these are all supposed to be lowercase. So let me just go through and mark that. Cool. So once we eliminate all the t's, what values do we have left? Well, we can kind of go through and just see, like, if we were taking the joint probability, what other variables we would have. And from here, we can see we would have u, v, w, and positive z. So that would be the factor that we have. So f2 would end up being u, v, w, and positive z. Cool. So then based on that, we can also write out our what we call remaining factors. So we would keep the one we didn't use, probability of y given v comma w, and then add on the factor that we just got. So f2 of u, v, w plus c. So those would be our remaining factors, and these would be the values that we get. So let me just box that. Cool. So now we've eliminated t, and the next variable we want to eliminate is u. So same thing, we're going to go through and see what factors have u in them. Well, right now it is just f2. So since it's just f2, we no longer really have to multiply or join anything together. Instead, we just want to eliminate the u by summing all the different possibilities. So that's why we can get that the factor f3 will be everything from f2 but the u, because we want to get rid of the u. And that would just involve summing up over all the possible values of u of f2. Then lowercase u, v, w plus c. So this is your factor, and then your remaining factors will be the factor that we didn't use, which is probability of y given v and w, and then our new factor f3, v, w plus c. Cool. So these will be your remaining factors, and this is your solution for part C. And then the next variable we want to eliminate is v. So we can look at the remaining factors that we have from the previous part and see that both of them contain v. So we will need to join them in some way first in order to get the fourth factor. So we can write out the fourth factor will be something. Not sure yet, so I'm going to leave that blank. And that will also put equal to the summation of all the different possible v values of the join between our remaining factors. So probability of y given v w and then f. Oh yeah, and this v is technically supposed to be a lowercase v, and then f3 of v w and plus c. Cool. And then based on that, our remaining factor will be equal to the w because of factor 3, then y from the probability, and then plus c from the factor 3 as well. So this will be your fourth factor, and then we can write out the remaining factors. Which will just consist of the fourth factor because we use both of the other ones in order to get this fourth factor. Cool. So then that is part D. And then we want to eliminate W. So we only have one factor and it does have W, so it makes sense, it all correlates well. So now we want to get the fifth factor by eliminating W, so I'm going to leave that blank first like before. And then you want to sum over all the possible W values of the fourth factor, so we can get rid of W, Y, and plus C. And that will result with the factor 5 being just Y and plus C. And your only remaining factor will just be F5, which is a Y and plus C. So yes, that is your solution for part E. And overall, we've eliminated all the variables except Y and plus C, which makes sense because if we look back at our problem statement, we are ultimately trying to find the probability of Y given plus C. So that's why we've gotten rid of all the other variables, so we just have terms regarding those two variables. And then based on that, let's look at part F. So we do have the factor F5 of the joint probability of Y and plus C, but how do you actually get the probability of Y given Z? So this goes back to the probabilities rules that we learned, specifically like the product rule. So what we want to do is, in order to get it, we need to divide and kind of renormalize this factor to be the given probability. So what that equivalents to is then we have the probability of like any specific Y and posit Z will be equal to the joint probability for that specific Y. So we can use the F5 vector, and then over posit Z over the joint probabilities for all the different Y's. So we have another summation, and then we can just call this like Y prime, F5 of Y prime, and then posit Z. So you will need this kind of like renormalization aspect in order to actually get the conditional probability, because right now we just have the joint probability. And in fact, when you do variable elimination, this tends to be the last step, because when you eliminate everything to the remaining variables, you usually have just the joint probability, and you will need to do this kind of renormalization or division in order to actually get the conditional probabilities. Well, So we satisfied our goal and found the probability of y given positive z. Now we have some questions in the other subparts that kind of just reinforces the understanding of variable elimination and how we can better it. So part G specifically asks for the largest factor size. So let's actually go back and look at the different factors we have created. So here, so first of all, the problem statement tells us that all variables have binary domains. So we know that for each variable, there are two different options, like positive or negative for the variable values. So that's why in terms of number of possibilities, there's two for each variable. So when we are trying to find the biggest or like the largest factor size, we are essentially trying to find the factor with the most number of variables. And then, so based on that, let's look through our factors. So F1 just has one variable because positive z is observed and given to be positive. So for positive z, there's only one option. So right now, our biggest is just one variable. And then for factor 2, we have 3 variables. And then factor 3, we have 2. And then factor 4, we have 2 as well. Factor 5, we just have 1. So then based on that, our largest factor is going to be factor 2 because there are 3 variables, each with 2 options. And that means the probability table will need to take into account all of these different options and end up having 2 cubed rows because there would need to be a row for each of the different combinations of options. So this will end up to being 8 rows, and that will be our largest factor. Cool. Okay, so then now let's look at part H, which asks, well, is there a better elimination ordering? And when we consider better elimination orderings, that just means we want an ordering where we have the smallest, largest factors. Okay, I know that sounds really confusing, but like we essentially want an ordering where like we minimize the largest factors. So right now, our ordering gives us the largest factor of 8 rows, but we want to try to lower that or minimize that. And this subpart is essentially asking for what ordering will allow you to do this. So usually when I get these types of problems, how I like to look at it is we already found that earlier it was factor 2 that gave us the largest factor. And factor 2 was given when we eliminated t. So now instead I'm going to go back up to the subpart where we eliminated t and see were there any other variables I could have eliminated first that wouldn't have expanded my factor so much. So here, for example, we could see that if we eliminated, say, u first, then our factor size wouldn't have become so big. Instead, if you eliminated u, you would have only considered the variables of here. And yeah, essentially just that. So because of that, we wouldn't have expanded to be like 8 entries. And since we are getting rid of u first, later on, this factor where we combine or eliminate t with wouldn't have u, so we would be restricting the value more to just 4 entries. So that being said, that means a possible ordering is just to switch the order that we eliminate t and u. So we would just want to eliminate x, u first, then t, and then v, w. And just having this switch lets us be the largest factor will just be 4 instead of 8. And that overall is better since 4 is less than 8. Cool. So this would be a possible solutions. And I just want to point out that for part H, there are multiple different solutions. So this is not the only one, but as long as the largest factor is less than 8, then we are fine. And usually the way to just solve these is to just go back and then try and kind of, in my opinion, like a trial and error approach of if I eliminate this first, how will that affect the factor that I was eliminating, and so on. So yes, that is the solution for part H, and that concludes problem 1. So then now we are going to move on to problem 2, which is on Bayes-Net, and specifically on independence. So since this is an independence focus, I wanted to go through and kind of outline some things you want to look at when considering independence, specifically what we call the inactive triples, which come into play with the separation. So essentially there are some like kind of layouts in the Bayes-Net that if this is the case, then you know that these two variables are independent already. So these are kind of the layouts you want to look for. So there are a few different ones. So the first one, for example, is what we usually call casual chain. And it's essentially just like a chain of nodes. And then we have X, Y, and Z. So in this casual chain, if Y is given, then we know that X is independent to Z given Y. And I'm just going to highlight that so that's more obvious. Cool. And then another thing we have is what we call common effect. And how that looks like is we have two nodes that all contribute to the same node. And then we have X, Y, and Z. So in this case, if it looks like this, then we know that X is independent of Z. So we do not need to know any information, but this is always going to be true as long as none of these variables are observed. And then the last one is what we call common cause. And that would be one node contributing to two different nodes. And then we still have X, Y, and Z. So in this case, if the common cause node is known, then we know that X and Z are independent. So then we know that X is independent to Z, given that we know what Y is. Otherwise, it will be dependent because it's literally contributing to the same thing. So these are kind of the 3 scenarios you want to remember, and specifically if these scenarios are true, then you know that these independent relationships hold. And then if they're not true, then you know that it is dependent, or it's not guaranteed to be independent at least. So yes. Cool. So then based on that, let's look at part A. So in part A, we have this graph and it's asking us which edges we need to remove in order for these independence relationships to still hold. So let's just go through and test whether these independence relationships hold or not. Cool. So if we look at A, B, and F. So this is if it's given F, so I'm just going to shade this F. And then we have A and B. So if we look at this, we can realize that A, B, and F kind of have like a common effect. Look, because if you trace the different kind of paths, you can see that well, B contributes to F directly, and then A will go through that path and contribute to F. And we can see here in this situation, the F is known. So that is actually opposite of the common effect that I have drawn here, because in that situation, we do not know what Y is. So because of that, we know that right now, this is going to be dependent. Or essentially that this independence relationship does not hold. So we will need to do kind of something along this path in order to fix it and for this independence relationship to hold. Cool. So that's a problem we want to keep out for. And then let me erase this. And now let's try looking at the next one. So A independent to F given D. So shading in D. Cool. So here we can see that what we have is kind of more like a causal chain because it's going through the different nodes. And we can see that if we have an intermediate node that is known, then it is fine. And these two values, A and F, will still be independent. So this is okay given the current setup. And then now let's examine the last one, which is B and C. And we can just see that B and C, here we have an example of common effect, but F is not known, so we know that this will be independent and it is fine. Cool. So the main issue we need to fix is to make A and independent to B given F. And our issue was that they're connected. So the easiest way is to just remove this AD edge, because if we remove it, the second one will still be independent since A is just kind of floating on itself and not impacting anything. So because of that, A will be independent to both B given F and to F given D. So that will solve our problem of this and make it independent. So that's why for part A, the solution is to have or to remove edge AD. Cool. Okay, so now let's do the same thing and look at part 2. So right now, let's first look at A, D, given B. So if we look at this scenario, we can see that, well, one path is AB to BD, and that would be a causal chain, and they are independent, so that is fine. But then we also have other paths to get from A to D. So here's an example where it is just A to D, and that shows that they are independent, which is a problem because it will always no will always be dependent on its parent. So kind of something I maybe to make us clear in the previous example is that when we are looking for these inactive and active triples, we have to consider all possible paths between the two nodes that are supposedly we're testing their independence. So if any of these paths have don't have any inactive triples, then that is a problem and we need to adjust it for some way. So right now, this is dependent. And I'm specifically going to note that the problem kind of is AD. And that's just to keep in mind, maybe it's something we need to remove later on. Cool. And then now let's look at A and F given C. So if we look at the different paths, so there's quite a lot, but I'm just going to look at, let's say, this one first, which is also a causal chain, and that is fine because we know that they are independent. But now let's look at kind of another causal chain type of path where it goes AB, BE, and then EF. So in this situation, we don't have an intermediate node that is known anymore because we are not passing through C. And that's an issue because then that means that they can be dependent. And specifically, the kind of problem is that we don't have a known node between these. So specifically, the kind of idea is that maybe you want to remove like BE or EF, for example, in order to kind of alleviate this problem so that we don't have this like crossover. And also another possibility is removing AB, because those are the different links along the path. Cool. And then, and there are a lot of other paths to get from A to F, but I'm just stopping at kind of the first dependent path that I see, because then I know it's already a problem and therefore don't really need to enumerate and try all the other ones out. And then the last is C independent to D given B. So right away, the first relationship I see is kind of just this common cause situation, and if we look back, if the common cause is known, then that will be independent, which is fine. So we know that that scenario is okay, but what are some other ways to get there? So we can see that we also have a situation where it is both are contributing to E, and that is also fine. And then we can see that another possible avenue is to go from this scenario, which will be like another common effect situation, which will also be fine. So for this scenario, you can like kind of enumerate all the different possibilities and find out that C will be independent to D given B. And yeah, cool. So it seems like we got to eliminate some of these problems in order to make them independent. So for the first one, it seemed like our main problem was with A given D. So I'm just going to go ahead and remove that. And then for the second one, we can remove any of these and they don't seem to really affect the other independence relationship. Yeah, so based on that, I'm just going to arbitrarily remove AB. But any of these possibilities should work. So then based on that, we would want to remove AD and AB. And this is just one possible solution. You can also remove like AD and EF, for example. Cool. And then now let's move on to part B. So the problem statement is that you're performing variable elimination and then with this base net, but you kind of just lost track of the relationships as you are joining. And specifically, you have these current factors that are left. And now we want to try to figure out what the edges are or what the possible combinations of edges there are. So before we determine the number, let's kind of see what these factors represent. So we have two factors, factors A and factors B, that are just individual variables. So because of these factors must have corresponded to just like the A node and the B node. And since there aren't any other variables involved, that means it wasn't like something given something, because then we would have at least like two variables in the factors. So because of this, we know that A and B are nodes that have no parents. So let me write that down. Have no parents. So there will only be outgoing arrows from A and B and no ingoing arrows. And then let's look at our next factor. So F of B, D. So this must have been gotten when we combine B and D in some way. And since we know that B has no parents, that means that there must be a connection from B to D. Because otherwise there would be kind of no relationship combining the two. Because in order for them to have this relationship, one of them have to be the parent of the other. So that means there must be an edge from B to D. Cool. And then our last factor is this big 5 variable factor. So C, D, and E. So we've already kind of considered factors with A, B, and D beforehand. So that means that kind of C and E must have a connection of some sort. So C and E must be connected, and by connected I mean like from one arrow, and then all the other factors must point to the parent among C and E in order for this to be true and to be able to combine to this 5 variable factor right away without needing the other factors. Cool. So then that means if we add up the minimum number of edges, that means that here these have no edges, and this will be +1, and then +1 for must be connected, and then for A, B, D have to go to C or E, and this will be +3. So that means that in total, the minimum number of edges has to be at least 5. And we can draw it out on this graph to visualize it. So we will have B going to D, and then among C and E, either can be the parent. I am just going to arbitrarily choose C as the parent, but you can flip it around too. So my arrow is going to go from C to E, but opposite is fine too. And then we just need A, B, and D to all at least connect to the parent of the C and E kind of isolation. So then here, here, and here. And then here are the 5 edges you have. Cool. And then now let's look at the second part, which now we want the largest number of edges. So notice that everything we talked about in this subpart, the first subpart, all still have to be true. So we know that we have at least 5 edges, and those will specifically be the 5 edges that we at least have. So let me just redraw them. Cool. But now I can see what additional edges can we have. Well, A, B, and D can also be connected to E. They just connected to E, and this factor would still happen, but it is not mandatory. So that's why we have our original 5 edges, and then if we plus the 3 of A, B, and D all becoming to E, this will give us a total of 8 edges. So that's why our largest number of edges is 8, and this is the resulting graph that you would get. So yes, that is it for the section, and yeah, have a nice day.